Good morning, everyone. Welcome to my talk. I'm Xiaowei. I'm currently Senior Director at Alibaba. Before that, I worked at Facebook, Microsoft, and Stratify. Alibaba has the world's largest e-commerce platform, Taobao. Hundreds of millions of users shop on Taobao every day. Improving the experience of our user is our top priority. So in this talk, I will give you an example on how we do that with search and recommendation. When a user does a search on Taobao, he usually looks at the listed in some of these. The goal of search is to help our user find the right product with the least effort. But what is right is different from one customer to another customer. So it's pretty subjective matter. To get everybody happy, we have to understand our users and the products better, and we will use machine learning to do that. When a user shops on Taobao, he interacts with our system. He does like look at a product, click a product, or even purchase a product. They become events, and they get captured and eventually ingested into a queuing system, such as Kafka. The idea is that we can use machine learning techniques to process events in such event queue to gain insights about our customers and our products. Because search is a very interactive experience. Our customer does a search, look at the result, click on a few such results, may come back, scroll, may even do more searches. We want to make sure that the insight we get from the user's behavior can be immediately used to optimize his search experience. So this is having a very strict latency requirement. And Flink is well suited for this job. Flink is a true streaming processor, which means it can provide high throughput with extreme low latency. It can achieve a latency of seconds or even sub-seconds. So we are going to use Flink to do real-time machine learning in our case. The first step in machine learning is pre-processing. The events that's collected into our event queue usually have incomplete information. For example, when a user clicks on a product, only the user ID and the product ID is captured in the event log. But such IDs do not really mean much. To gain a full picture of what really happened, we need to join such events, look up such events in entity tables such as user profile table and the product tables. Because we are doing such join in a streaming fashion, we need to store such entity tables in a system which is really good at point lookups. And we decided to use HBase for that. So Flink does a streaming join between the event string and the entity tables, such as the user profile and the product tables. Then we get a better picture, a full picture of what happened. We do further cleanup of such events. Then we try to calculate real-time features. These real-time features can include things such as the inventory of a product, or we may even decide to do aggregation, such as calculate the number of clicks for a product in the last hour, last 15 minutes, or last 5 minutes. Such real-time features get pushed to our online search and recommendation systems and are used by the rankers to optimize the ranking and the experience for Taobao users. This is part of our pipeline. Another part of our pipeline is that we also do online training. So in this case, we are going to treat any impression events as negative samples, but a click event or purchase event can be treated as a positive sample. So with Flink, you can use any of your favorite online learning machine algorithms and train your models online. We will validate such online models from time to time periodically. Once a model passes validation, it gets pushed to our search and recommendation systems and can be used to give an even better experience for our customers. In some cases, the online training itself can bring very good result. For example, on Singles Day, which is the Chinese version of Black Friday, we observed a 20% jump in sales from search simply by using this online model. So the difference can be dramatic. So this whole pipeline looks pretty straightforward. With Flink, we can do real-time machine learning. But the world is always slightly more complex because we cannot expect our AI engineer to get things right in one shot. It's unlikely we will find the perfect model with just one try. So in reality, it's going to be a lot of iterations. And let's take a look on what it takes to do such iterations. This is a rejoining of the previous architecture diagram. Again, Flink subscribes to event logs, the behavior events from Kafka, and it will join such event strings with the entity tables, such as the user profile or product tables, which are stored in systems like HBase or Cassandra. Then Flink does calculates real-time features as well as train real-time models. These real-time features and models get pushed to our online search and recommendation systems to optimize the experience of ranking. When our AI engineer pushes the model into production, he wants to find out if the model is performing better than existing models. For that, he will need to do A/B testing. And he wants to see the result, how his model is performing at real time, and he wants to have a real-time dashboard for such performance. Flink is, again, well suited to do that. Flink will collect all the metric for each model and save such results in HBase. Then our AI engineer can use a dashboard to query HBase to see how each model is performing. He looks at the dashboard and figured out that his model is not performing exactly as he wished. Something is not perfect. So he wants to figure out what went wrong and try to tune his model. For that, he will need to do a lot of data crunching and a lot of analysis. If he tries to do such analysis with a system like HBase or Cassandra, it's going to be extremely inefficient and can be very slow. So we decided to store such kind of data in a columnar store, such as ClickHouse or Druid. With this system, our AI engineer is able to send analytic queries to ClickHouse and Druid and expect the answer to come back very quickly. So he plays with it and do all kinds of analysis using the real-time reports, and eventually figured out what went wrong with his model, and he even come up with a potential solution. So he decided to try out his new model. He can wait for new samples to come, but a more efficient approach would be he can train the new model using the historical data. So we also save the historical data in an offline data warehouse such as Hive. And then our AI engineer can use batch processing to do the pre-processing and use offline training to validate his new models. As we can see here, we started to store data in multiple storage systems. Whenever this happens, sooner or later, you will need to run a query that joins data from multiple systems. So we needed federated query support, and we use Drill and Presto for that purpose. This can also be used to do batch acceleration, meaning speed up query performance for data that is stored in Hive. But no matter how good your acceleration is, there will be a query that's too complex to calculate on the fly. For that, we decided to run such expensive queries periodically. For example, like once every 5 minutes, and store result in a caching system like Redis or MySQL. Then when our AI engineer need to run such a query, he can just query the caching system and get result immediately. This can speed up the iterations. As we can see here, even though the original real-time machine learning pipeline started pretty simple and straightforward, but if we really want to push such a pipeline into production and make it efficient, the architecture becomes more and more complex very quickly. This is not a coincidence. We have observed this same pattern over and over again. Whenever you try to build a real-time data pipeline, sooner or later, it will become something like this. So the question is where does this complexity come from? And is there a better way in doing this? So let's take a step back and look at what is the fundamental reason for this. The first thing to build a scalable data warehouse is batch processing. Batch process all the data and produce a complete result. The downside of batch processing is that your application is making decisions based on data which are hours old or even days old. Lambda architecture proposed a speed layer to fix this problem. A speed layer will process new events in a streaming fashion and produce incremental updates to the result that is produced by the batch processing. Our downstream applications can combine the result from batch processing and speed processing to get the final result. But the result produced by batch layer may not be efficiently queryable by our applications. So Lambda architecture further proposed a serving layer, which will organize the data in a way that can be efficiently queried. So our downstream applications will combine data from the serving layer as well as the speed layer to get the final view of the current data. There are two potential problems. There are two problems in this architecture. The first problem is that we are using a different system for batch layer and the stream layer and the speed layer. This can introduce a lot of complexity into our system. One great achievement of Flink is that it's a unified processor which is good at both batch and stream processing. So we can use a single system that does both. And the Flink will guarantee that the semantics of both batch and stream processing are compatible with each other. The second problem in this architecture is that the data is stored in potentially different systems. The result from batch processing is stored in a serving layer, and the result of stream processing is stored in the speed layer. This can also cause complexity in the system. Let's first take a look at what are all the possible choices to store our data. So if you look at the open source world, there are actually lots of choices in storing data. For example, we can use Hive to store offline data. HBase and Cassandra are very good at storing real-time data and provide efficient point lookup query abilities. And on the other hand, Druid and ClickHouse are good at serving analytic queries. While the choices are always good, but in this case, it's actually indication that none of the choices above is good enough to meet all the requirements from Lambda architecture. As a result, our application developers are forced to use multiple such systems. And when this happens, the data, we will have data islands. The data may need to be duplicated between different systems, and this will increase your hardware cost. In addition, when it will always be a challenge to maintain the consistency of data among different systems. So this will also increase the maintenance cost. When you are dealing with multiple systems, each system will have its own pitfalls, and you will need to run through such pitfalls, and it can be a steep learning curve. So we are hoping that we can have a single storage system that can do this. So ideally, we will have an architecture just like this. We will use a unified processor which does both stream and batch processing. Flink is such a processor. It can do both batch and stream processing efficiently. Then the output from this unified data processor is going to be stored in this unified storage system, which serves downstream applications. This over the last couple of years, there has been great advancement in this direction from various data lake solutions. A data lake solution usually stores data in a cloud storage, such as S3 on AWS or OSS on Ali Cloud. It can store, a data lake solution can store both raw data, raw ingested data, and on top of that, we can do incremental ETL and produce other tables. All such tables can be queried by query engines and serve downstream applications. This is going to simplify your architecture a lot, but there are two areas for improvement in this approach. The first area is that the data in current data lake solutions are not always fresh. They have a latency of minutes or even more. This is probably the best thing you can do if your upstream data processor is microbatch based. But in our case, we use Flink as our data processor, and Flink is a stream-first data processor. Not making the data immediately available to downstream applications would be a missed opportunity. The second area for improvement is that in current data lake solutions, the access pattern is usually geared toward analytical workloads. So, but as we see in our real-time machine learning pipeline, point lookup queries are as important as analytic queries. We need to use it to serve downstream applications as well as do streaming joins in Flink. So to address both problems, we are proposing a new paradigm. We are going to propose, this is called hybrid serving and analytic processing. In such a system, it will provide a unified data storage for data produced by both batch processor and stream processors. It is capable of ingesting real-time data at extreme high rate, could be as high as tens of millions of events a second. It will make data available to downstream applications immediately without any delay. So the data is always fresh. On the other hand, this system will also offer a unified data storage for all important real-time data access patterns. On the bottom of the slide, I have shown a classification of different data access patterns. On the rightmost, we have the transactional workload, which has the most stringent requirement in terms of latency and SLA. Then we have the serving workloads, which includes simple queries such as point lookup queries. These workloads usually have a very high QPS requirement and also strict latency requirement. The latency could be as low as tens of milliseconds or even milliseconds. Then we have the analytic workloads whose QPS might be a bit lower, but the queries are much more complex, and our users still expect the query to finish within seconds or even sub-seconds. On the leftmost, we have the batch workloads, which does not have a strict expectation in terms of latency, but does need to process a vast amount of data. So HSAP will cover the data access pattern in the middle. All the real-time needs for serving and analytic query patterns are going to be supported efficiently with HSAP system. With the HSAP system in place, our architecture will now look like this. Again, we use a unified data processor for both batch and streaming jobs. Then all the output from these jobs were going to be stored in this HSAP system. The HSAP system serves all downstream applications. For example, it can support real-time dashboard, support real-time reports, and other real-time applications. But one interesting thing about the HSAP is that because it's good at analytic workloads as well as serving workloads, Flink can store the entity tables in HSAP system as well and use HSAP system to do streaming joins. So we really have a unified storage for our real-time data now. Over the next few slides, I'm going to explain how we are going to build such a HSAP system at Alibaba. When you start building a new system, the first thing you need to consider is what is the interface to your users. And we want the learning curve for our users to be as smooth as possible. So we decided to leverage existing ecosystem. And in this case, we choose Postgres. Postgres has a very complete support for all the functionalities that we need. And it also is very popular in this domain. By being compatible with Postgres, we gain a lot of value. For example, all the tools that is available for Postgres can be used in our system. You can use JDBC driver for Postgres to connect to our server. Our protocol is compatible with Postgres. You can use tools such as pgadmin from Postgres to connect to our server, query our server, and manage our server. You can use even use your favorite BI tool, such as Tableau, to do complex BI analytics with our system. Another big advantage of being compatible with Postgres is that all the documentations out there about Postgres can be used for our system as well. For example, if you ever wonder how to express some functionality in Postgres in SQL, you can do a search on the internet. The chances are you will be able to find the answer. I find myself doing that from time to time. And another big advantage of Postgres is that it has a lot of third-party extensions. These extensions can extend the functionality of Postgres itself. Because we are compatible with Postgres, it makes it possible for us to extend the functionality of our servers easier as well. The system we are building, the name of the system we are building is Holograph. I just explained the Postgres part. The holo stands for holographic. And let me spend a couple words on this. A black hole has an event horizon. For any object that enters the event horizon, the object can never come out again. It's lost into the black hole forever. Imagine that you are throwing a book into a black hole. Once the book crosses the event horizon, it can never come out. So the question is, what happens to the information that is contained in the book? Is that lost forever? That appears to be the case because you can never get the book out. But this is problematic. It violates one of the fundamental principles in quantum physics. In quantum physics, information is a conserved quality, just like energy. It cannot be destroyed or created. So if the information in the book is lost when you throw it into the black hole, it could be problematic. And this question has puzzled physicists for many years. And eventually, they come out with a potential solution. The idea is that the world is holographic, which means the three-dimensional, even though the world looks three-dimensional, but if you look at the surface, the boundary of this three-dimensional space, the boundary actually encodes all the information in it. If you look at a hologram is a spatial type of two-dimensional film, but it actually encodes all the information about the three-dimensional object. So if you look at a hologram from different angles, it can show you the three-dimensional object from different perspectives. In this case, the boundary of a black hole, which is its horizon, this two-dimensional surface, will encode all the information that is contained in the black hole itself, which includes all the information inside the book that we throw into this black hole. In our case, you can throw all your data into Holographs. Holographs will be able to store all your data, but at the same time, you can retrieve any information you want from holographs from whatever perspective you want. So now let me explain the architecture of holographs and the challenges we have in building holographs. This is the overall architecture diagram for holographs. You can your BI tools, your applications can connect to holographs using PostgreSQL protocol. It issues a SQL which is compatible with Postgres, and that request gets into a load balancer which chooses one of the front-end servers we have. This front-end server will compile the query and optimize the query and generates a query plan. A query plan has a lot of query fragments. These query fragments gets distributed into a set of black hole servers. The black hole servers does the heavy lifting of doing the query processing. And the data are stored in a distributed storage such as Pangu or HDFS. Now let me go into more details about each component. The first design decision we made is we are going to build a cloud-native system. We are going to use storage computer disaggregation architecture. Over the last couple of years, there has been tremendous advancement in terms of network technology. 10 gigabytes network has become commodity. We start to have 25 gigabyte, 50 gigabyte, or even 100 gigabyte network now. So throughput is largely not an issue. It's possible to store the data in a different machine from where you do the computation now. This architecture gives us two main advantages. The first advantage is that when you are running out of storage space, when you need to add more storage, you can simply add more storage node. And if you are running out of compute capabilities, you can simply add more compute node. This is especially convenient in a cloud environment where resource is very elastic. You only pay for the resource that you really need. The second advantage in this approach is that it makes the operations much easier. For example, imagine that in the old days, if you want to add more computation node, you will need to add a new machine, but before it can serve any traffic, you need to migrate data to this new node. Data migration is always complex, and it can be slow. But in our new approach, when we add a new computation node, it will be able to serve online traffic immediately. Even though the advancement of network technology has largely solved the throughput issue, but accessing data from a remote system will always have some latency. If we do not do it carefully, latency can quickly become bottleneck for the throughput of your system. To solve this issue, we decided to use a completely asynchronous framework to hide the latency of remote data access. With this approach, the throughput of our system is only determined by the throughput of remote storage itself. It's not going to be sensitive to latency from accessing remote storage. Modern hardware also have lots of processors. To make use of such processors, people use threads, and we will need to write thread-safe programs. And the common practice is to use locking. But whenever you introduce lock, it adds contention to your system, and your system is not going to scale efficiently because you are wasting a lot of CPU cycles spinning on locks. We adopted a cooperative scheduling mechanism. And with such a scheduling mechanism, we can conclude that a piece of code can never be switched out. So we actually do not need to take lock at all and still be thread safe. This can greatly improve the scalability of our system. Modern hardware also have lots of memory. Being able to efficiently use the memory is a critical part in having a performant storage. We have very sophisticated memory and cache management system, which makes the best use of our memory. So let me talk about the query processing or compute part for holographs. As a HSAP system, holographs need to serve a very diverse set of real-time workloads. These workloads include complex analytic queries, as well as simple solving queries. When this happens, we do not want the big analytic queries to block the processing of such low latency point lookup queries. So we introduced our own custom scheduler to guarantee the SLA for individual queries to make sure our point lookup queries can still return within milliseconds, even when the system is loaded with a lot of big analytic queries. On the other hand, if the system is only having a single query, we still want to make sure this single query can use all the hardware resources in this cluster to process the query to finish the computation as soon as possible. Fortunately, the cooperative scheduling mechanism and the asynchronous framework that we put in place allows us to launch massive parallelism with very little overhead efficiently. So we can a single query in our system can make full usage of all the hardware resources in our cluster. Our query engine is also very efficient in leveraging processors. We use vectorization technology. We make use of SYNC instructions. We optimize for AVX512 instruction set. Our query engine has a very deep understanding of how data is stored in the storage system. So we do optimizations for such data storage, and as a result, we see very good improvements in terms of query performance. Both of our query engine and the storage engine is developed in pure C++ native code. And the performance, as a result, we get very good performance. For example, for point lookup queries, for serving scenario, for point lookup queries, we outperform HBase by an order of magnitude. And for complex analytic queries, we outperform Greencrown by 3x. Let's take a look on how our system looks like with this new architecture. Again, we will use Flink to do our real-time machine learning as well as offline training. But the difference is that now we can store all the data in a single system, holographs. The holographs is stored to store the entity tables such as user profile and the product. It can also store all the samples about that is produced by Flink. It stores the metrics from A/B testing. So our AI engineer can use real-time dashboard to issue point queries against the holographs to retrieve how his model is performing. He can use real-time reports, leveraging a BI tool such as Tableau to issue analytic queries against holographs to understand why his model is performing a certain way, to gain insights about his model. And if he wants to try out different model, he can talk with holographs to get the data and do offline training to try out his model. So with this system, you can see, and furthermore, the holographs is also used by Flink to do streaming joining because it's very efficient at doing point lookups. As we can see, with holographs, the architecture of our system gets simplified a lot. It will make the iterations of our AI engineers much more efficient. And the holographs is not only serving internal customers at Alibaba, but it's also available publicly on Ali Cloud. Now we have a quick summary. In this talk, we proposed a new architecture, HSAP system. It will greatly simplify your application development. At the same time, a HSAP system is very good at ingesting data at extremely high throughput. It will present the data, it will always present fresh data without sacrificing performance and scalability. When your application, when your business makes decisions based on real-time data, you are getting more values out of your data. So this can boost the performance of your business, just as we did with Taobao. At the same time, the ground-up new design and sophisticated optimizations that we did in Holographs will help your business reducing your TCO. So in short, with Flink and Holographs, you can make your business real-time without any compromises. Thank you.